Okay, ladies and gentlemen. Well, welcome to this very special lecture, and I thank you all for coming. I hope as many of you are recovered from the convention. They'll be there eventually. But first we have an important announcement. I'd like to welcome and introduce our new Canberra Skeptics new president, Lawrence Krauss, to say a few words.
2013 has been a fantastic year for Canberra Skeptics. The convention was a resounding success, so thank you to Kevin for all his work and the committee for the rest of that. Looking forward to 2014. If anyone isn't on our mailing list yet, please email mail@canberraskeptics.org.au. You can follow us on Twitter, Facebook, or join us on Meetup as well. And so we're really looking forward to bringing you wonderful evenings just like this one next year. Thank you very much.
And now on to tonight's speaker. Well, tonight's speaker is Professor Lawrence Krauss. Professor Krauss is a renowned cosmologist and Foundations Professor and Director of the Origins Project at Arizona State University. He is the author of over more than 300 scientific publications and 8 books, including the best-selling The Physics of Star Trek, and the recipient of numerous international awards for his research and writing. He received his PhD in physics from the Massachusetts Institute of Technology in 1982 and then joined the Society of Fellows. In 1985 he joined the Faculty of Physics at Yale, moving in 1993 to become chairman of the physics department at Case Western Reserve University before taking up his current position at ASU in 2008. He is a frequent newspaper and magazine editorialist and appears regularly on radio and television, and we are absolutely delighted to have him back. So, please welcome Professor Lawrence Krauss. First off, we would like to acknowledge the traditional owners of the land on which we meet today, the Ngambri and Ngunnawal people, pay our respects to their elders past and present. Now, tonight is a question and answer session, so it's up to you, ladies and gentlemen. If you've got some interesting questions, please feel free to fire away. Questions relating to the Higgs boson will be not taken kindly, because last time we asked about the Higgs boson, he took up half the lecture on that one question.
I'm happy to do that again.
Okay, so I'll start off with the first question. If you want to have questions, just put your hand up and either Amanda or Nick will come see you. Professor Krauss, what, in your opinion, was the biggest scientific discovery or event over the last 12 months?
The Higgs boson.
That happened over 12 months ago, I believe.
Well, it was confirmed less than 12 months ago. By the way, in my affiliations, you should mention that I'm also a professor at Australian National Universities. So I think that's a relevant thing for this audience. I have a position here as well, which I'm very proud of. Let's see, other than the Higgs boson, in the last 12 months, there's been a lot of interesting news regarding space, regarding Mars from the Mars rover, about the nature of the planet and the possibilities or impossibilities of life on Mars. I think that's another huge result. And there's also been a lot of interesting results in another field, not physics, but or astronomy, but on our evolutionary background, on hominids and our relationship to other hominid species. That's been confusing, and that's wonderful, as I often say. If you're a scientist, that it's best state to be in is confused or wrong, because there's something to learn. And we're very confused about hominids, because much of the conventional wisdom about our relationship to both Neanderthals and others, and the history of the movement out of Africa of humans and of Homo sapiens and Neanderthals and there's other species called Denisovans. All of it with recent DNA evidence has really gotten screwed up, and so it means that well, it's not too surprising, and it's the same thing when you also look at the universe. As we try and look at the universe, anytime we have sparse data, we're likely, you never know if what you're seeing is just an anomaly. if you have one or two events, that's why epidemiology is so useless on the whole, because a large medical study is 3 patients usually, and it's hard to generalize from that. And so we have one universe that most of us live in, and when we see things like rare events, for example, in dark matter, there was a claimed discovery of dark matter, 1 or 2 events in an underground detector, a more recent experiment that can now look at with the larger samples, and no, it's just an accident. And accidents happen all the time. Now, if you're trying to determine our lineage as humans, as I often say, in Phoenix the other day, I was saying that if you happen to discover a skeleton of a basketball player in Phoenix and my skeleton, 100 million years from now, or 5 million years from now, or whatever, you'd say we were a different species if you didn't know any better. Unless we were both, in the same place and got killed in the same place, and then you might change your mind. And that's exactly what's happened. From 1 or 2 samples, often species are established, and now we're thinking that maybe those were premature. So that, anytime we're wrong, I think it's interesting. And the results on Mars have been up and down. There's definitely water on Mars. Whether it was suitable for life, there's new evidence for a lake on Mars that you may have just heard a week or 2 ago. I was just talking to CNN about it the other day. And that's interesting, although I suspect, given the nature of the lake and how long it was there, that whenever you think of water and organic materials, you think life, but on Earth, life evolved probably. Well, you also need more than water and organic materials. You need a rich source of energy. And the deep ocean vents on Earth were probably the most likely places for life to form, and that certainly wasn't the case on Mars. So anyway, but there's lots to do. Anytime we open a new window on the universe, it's exciting. And the new window on Mars is exciting. The new window on our ancient humans are exciting. And of course, the most exciting thing in all is the new window on the fundamental structure of matter. And the confirmation, and the definitive confirmation, a year or so ago when we talked, it was just sort of sounded like it might be a Higgs particle, but now it looks like a Higgs particle, and we're waiting. And that's got us primed for what's next when that Large Hadron Collider turns on a year from now, 2015, a little year and a half from now, to really look and maybe reveal a whole new universe, literally, perhaps even maybe new extra dimensions. So that wasn't the whole time, but there we go.
Thank you very much. Okay, questions from the audience now.
Good, because I'm going to go over for dinner if you don't have any, so that's good.
All right. Yes.
I saw a story recently that the dinosaur-killing asteroid might have splashed fragments of life into space and onto Mars. So any comments on whether that's actually possible or not?
Oh, sure. Yeah, I mean, that's the interesting thing. What's interesting about this recent observation of a lake on Mars is that the age of the lake, Mars was formed by impact. It was an impact crater. And comets delivered, there's now much better evidence that comets delivered most of the water on Earth. We used to think it wasn't the case because the isotopic abundance was different of deuterium on comets than it was Earth. But there's enough material water that's been bombarding the Earth in the last 4.5 billion years to account for all the oceans. And now it looks like that probably comets from the outer solar system have the right isotopic abundance and they could have done it. So, but anyway, this lake formed where this crater formed about 3.8 billion years ago. And what's interesting about that is that was right around the time that life was forming on Earth. The oldest fossils, some of them in Australia, are that age. And so while I think personally that it's highly unlikely that life would evolve in that particular environment that they just recently discovered on Mars, Mars pollutes Earth all the time, and to a lesser extent, Earth pollutes Mars. So the big surprise would be if we discovered evidence for life elsewhere in our solar system, as I expect we will. Maybe not extant life, but extinct life, microbial life. It would be a huge surprise if it wasn't our cousins. Because no planet is an island, as I like to say. We pollute, and if you look at inside a rock, the 6 to 12-month journey between the planets, microbes can certainly exist in that environment to make the traverse. It's a little easier to come from Mars, and that's why it's potentially more likely that Mars seeded life on Earth. Mars, if life evolved on Mars at early times, it could have easily seeded life on Earth. And so, as I often say, if we discover, if you want to look at Martians, just look in the mirror. So whenever a large comet hits, it splashes things out, and some of the ejected can get the escape velocity. The escape velocity on the Earth is a lot bigger than Mars, and also you have to be able to head out instead of in towards the sun. That's why it's more likely. We measure Martian meteorites all the time here on Earth. The easiest place to find them is Antarctica because it's white, and that's the only reason why people. It's not magnetic fields or anything else. It's just it's white. And if you drive around a Skidoo and you see something that isn't white, it's a meteor. And that's where we discover a lot of meteors, and a lot of pieces of Mars have been discovered there, but other ones elsewhere too. And we know that because we've sent rovers there. We know the isotopic abundance materials, and in fact, I almost recently bought a little piece of Mars, but it was too expensive that they were selling at my university. So it's certainly possible that life goes between the planets. And so it would really be fascinating if we discover evidence for life to see if it had a different kind of structure. Although I suspect, from what we've done at my institute, looking at the origin of life at my institute, as an educated layperson in that area, it looks to me, I would be amazed. I do think that the route to life is pretty well unique. I do think that the use of ATP, the base pairs, the RNA world turning to a DNA world, I suspect that that's driven as much by chemistry, in a unique sense. So I wouldn't be surprised, even if there was a separate genesis, that it had a similar. We'll see. I mean, we don't know.
I was just wondering, what do you think Einstein's greatest theory or contribution was? And if it's a theory, could you explain it in layman's terms?
What Einstein's greatest contribution was?
Yeah.
Well, there's no doubt that Einstein's greatest achievement, not your contribution, his greatest achievement was a general theory of relativity. It was a complete, it was an amazing piece of intellectual activity, pushing the boundaries of what was known mathematically at the time. But it's also a new theory of gravity, and it also changed our picture of space and time more than anything else. Special relativity told us that space and time are related. But general relativity said that space and time are dynamical, that they respond to the presence of matter, that space curves in the presence of matter and expands and contracts, as does time. And that was profoundly important, and of course it was essential, because we could not have a consistent theory of an expanding universe without general relativity. It doesn't work in Newtonian mechanics. So while Einstein got it completely wrong, he thought his theory could only work if the universe was static. He was completely wrong. In fact, it generally predicts an expanding or contracting universe. And it's the only consistent theory that could have done that. So all of modern cosmology would not be possible without general relativity. Plus, by the way, for those of you who got here by GPS, you wouldn't have been able to get here without general relativity. Because the amazing thing is that, as esoteric as it is, it's essential for your GPS to work. Because general relativity says that clocks tick at different rates in a gravitational field. And if you actually work, and so the GPS works by satellites 8 or 10,000 miles above the Earth, moving fairly fast, and there's a special relativistic effect. But by far the largest effect is the fact that they're atomic clocks, and they're ticking at a different rate than the atomic clocks on Earth. And the way GPS works is two satellites take look at a given location and find out the time that it takes to get the light to bounce back and forth, and using those trajectories, and they're able to figure out, if you have three of them especially, figure out where you are. But they go out of sync in a period of about 15 seconds. Certainly within the accuracy of GPS, and within an hour, you'd be tens of kilometers away if you didn't take into account general relativity in those GPS things. So every time you use your GPS, you're relying on general relativity.
Hi, you were talking about Mars just before, but there are other sites around the solar system which may be even more
better. They may be much better source of life.
So
Europa,
I think
for example,
Europa, yeah.
or EO even.
So, is this somewhere we should be targeting in our space?
Yeah, it's just harder. All of this, by the way, should only be targeted without humans. Humans are a waste of time in space. No matter what anyone says. We are 75 kilogram bags of water. We are meant to be on Earth and not in space. And so we can do much more with machines in space. And some of my colleagues, especially those who are beholden to NASA, don't agree with me, but they're wrong. This is usually the case. No, anyway, and so and also in a place like Europa, we can't send astronauts. We can imagine sending astronauts to Mars. It's an environment you could imagine people being on, but not to Europa. And so the trouble with Europa is it's got huge oceans, and they even exchange energy. Now there's been some geysers just recently this week seen from Europa. Jupiter the tidal forces of gravity going around Jupiter generate enough heat for those planets to have liquid water underneath the surface, and there are organic materials on in those planets, in those moons. And so it could be an ideal environment, but you'd have to drill down, a mile or two of ice, and you have to go to there and then drill down and then try and search. And so it certainly there are proposals for missions to Europa. And it would be very exciting to do, and I think it's certainly more exciting from a scientific perspective than sending humans back to the moon, although I suspect we'll spend more money on the latter, especially now that China has sent a rover to the moon, because the space race is driven more by politics and science. And the fact that China done this, I suspect, will prompt the United States to do some response. But Europa, there's EO is another, there's lots of interesting possibilities. And Mars is just, it's just low-hanging fruit in some sense. It's easier to get to, you land on, and you can run a rover on it. And but we will make, eventually, if we have enough money, send the programs. But the problem is that the really interesting programs get cut out because the human program costs so much money. You got to keep humans alive for some reason. People like it, and that costs a huge amount of money. It costs most of the money of a mission. And the International Space Station, this boondoggle in the sky, is $150 billion. And as I often say, the best science we could do for it is to let it splash into the ocean and see how big a wave it makes. Yeah, thanks.
So given the uselessness of the human body, what are your thoughts?
It's useful on Earth.
In space travel. What are your thoughts on the proposals of a manned colony on Mars?
Well, I was just talking about that on CNN just yesterday, the other day. Well, look, I actually wrote a proposal that's in the New York Times 4 years ago saying if we sent astronauts to Mars, there should be one-way missions. And not only because there are a lot of people that I would like to send out, but because it just costs too much money. Almost all the cost, over 95% of the cost of a round-trip mission to Mars is the way back. Plus, we don't know how to do it in a way that won't kill the astronauts. The radiation for a round-trip mission would exceed, well, at least it would produce cancer. It would exceed the limits that are allowed. So there's cost and safety. So if you're going to do it, you want to send them one way, and then say, okay, well, we in fact, after I wrote that piece, I got this astronaut named Buzz Aldrin, and some of you may remember, contacted me. We testified together before Congress years earlier. And he was very in favor of it. He told me that Chris Kraft, and those of you who are old enough to remember, like me, the moon missions, because I was fanatically interested in them when I was younger. Chris Kraft was the voice of the Apollo, of mission control. He had actually calculated that you could send a single mission to Mars and leave them there and provide them with supplies for the rest of their lives for about 1/20th the cost of a single round trip. So that's interesting. On the other hand, it's just still pie in the sky, because Mars is still a very hostile environment. In particular, the radiation on the surface of Mars means you couldn't live on the surface. You'd have to live underground. And I think when you tell people, well, okay, you're going to spend the rest of your life living underground, you can go out two or three hours a day, maybe, and not get cancer for the rest of your life, and then it becomes a little less attractive. But I think it will happen someday. I suspect we will send humans to Mars, because sending humans into space is much more for adventure and national pride. And I suspect, some country like the United States will want to be the first country with a permanent colony on Mars. But all these people who think it's going to be done in your lifetime, I think are really, it's very expensive, and I can't, it's exponentially more expensive you know, you can send people on vomit comments. I know this guy Richard Branson, and he likes to send people on these vomit comments and charge them $100,000. And then, but it's exponentially more expensive to get into near Earth orbit, and exponentially more expensive to escape the Earth, and then to have something that would actually survive that. So it's just, it's hard for me to imagine anything other than a government or multi-international. I can't see private enterprise doing it, at least doing it for profit. I mean, you may have some crazy billionaires who are willing to, but it would cost, it's still, we're talking $100 billion, I bet, at least. And that's real money. And even then, as I say, it's not clear we have the technology to do it easily, quickly enough. So if it's going to happen, it's not going to happen in 2025, which is what they claim. I mean, that's just around the corner. If you wanted to do a mission for 2025, you have to start really preparing for it now, and you have to have the infrastructure and the manpower. So maybe, you know, maybe it'll happen in your lifetime, maybe. And it only makes sense. It indeed does only make sense to send people one way. That part I agree with completely. Yeah.
How did you make a name for yourself in the world of science, and what's your advice for a student such as myself to make a successful career out of science?
Well, I worked hard. I think that's about 90% of it. I think. Well, and also I enjoyed it. I think my advice to young people who are talented is to first of all not let your teachers get in the way, not let them dampen your enthusiasm, and to not give up. I mean, science, you know, in the new movie that Richard and I made, which some of you may have seen, there's a dialogue where we go back and forth and say science is fun, and it is fun. But the point is it's hard work, and not only is it hard work, most of the time you're not making any headway. It's not true for just science, it's true for almost any kind of research. Most of the time you're not making any headway, and that can be very, very frustrating. And so you have to be willing to keep beating your head against the wall and keep trying and keep trying. And also to realize that it takes all types. So we have stereotypes of scientists. And those stereotypes are sometimes true, but they're not generally true. Science takes all types. You don't have to do theoretical physics even. You don't have to be a mathematical wizard. You have to have mathematical aptitude. But there are well-known scientists, friends of mine who I know, some Nobel Prize-winning scientists, who are not mathematical wizards. I mean, you know, that kind of thing is as much luck as anything else. But you just keep plugging away. And you do it as long as you enjoy it. The only reason that I know that scientists like me, who do kind of useless stuff, continue to do it is not to save the world, but because we enjoy it. And I think as long as you continue to enjoy it, you should just keep plugging away. Now, as we call it that, some people say, well, how, you know, I like your career of, you know, becoming a, whatever I'm called, who speaks to the public. How can I do that? And again, I tell young scientists that if you're interested in communication and writing, well, you should always write. Writing you need to do. And I wrote tons when I was a graduate student and postdoc. I never saw the light of day. I used to submit to New York Times all the time, and all I'd ever see was actually other bylines with my titles from the writers of the New York Times, which was suspicious. But anyway, but I did it because I needed to do it, and I think you need, if you're going to want to be a writer, you have to continue to write. But the main thing is, if you're a scientist and you're talented, then the best thing you can do is science. And if you're interested in communicating, you can take advantage of those opportunities. And the more distinction you have as a scientist, the greater the opportunities are, and the larger the soap opera. And you know, in terms of my own accomplishments, well, you know, it's a bunch of different areas I'm proud of. And sort of dark energy was, for me, the most satisfying of the fact that we realized that the universe should be dominated by the energy of empty space well before my good friend Brian Schmidt here actually discovered it. And I'm sure he didn't believe it. That was very satisfying to me, right? I mean, it's really kind of surprising when you are, because most of the time you're not. Anyone else? No.
So speaking of science communication and dealing with trying to help the public understand the role of science and the variability of science, how do you help people understand, number one, what you talked about at the beginning, that we thrive on being wrong rather than being right? How do you help? Because, you know, I think the general public looks at us whenever there's 2 or 3 different theories. They're like, well, you guys don't know what you're talking about.
Exactly.
How do you explain that? And then the other question is, how do you explain the idea of all the uncertainty that we have to deal with and try to...
Well, uncertainty, you hit two very important points. In communicating with the public, those are two of the major misunderstood areas of science. The point is that we... the fact that we can find out we're wrong is wonderful. In many areas of human activity, we don't even know if we're wrong. And the fact, so science progresses, but it doesn't progress by something being right and then being wrong. That's the biggest misunderstanding. Something that's right, and by right, I mean that it agrees with nature. You model nature, you make the correct predictions. That can never be wrong. It can be subsumed in a larger theory that changes it, just like Newton's law of gravity got subsumed in general relativity. But the fact that we can, and it amazes me, especially since lately I've been dealing a lot with religious issues for some reason, the fact that we can change our minds is somehow viewed as a fallibility.
Yeah, I know.
And what we do when we teach science completely incorrectly. We teach it as a set of facts, when that's irrelevant. Okay? It's a process of how to distinguish sense from nonsense, how to ask questions. And we really need to base our teaching more on the asking of questions and not knowing the answers is great. I was just talking to someone who was asking Q&A some other place I was in the States recently, I forget where, a parent and talking to his kid. And you know, we as parents, we tend to not want to say that we don't know the answer. But the best thing we can say, don't know the answer, let's see how we might find out the answer. Because that's a skill that will be useful. The set of facts is useless. But the skill, the process of asking questions and sifting through information and trying to distinguish what's sensible and nonsensical. But the other point is uncertainty. Uncertainty is also viewed, especially in the case of the present climate change issue, as being and I wrote a piece on this, or at least did an interview about it, because the fact that we can quantify the fact that we have uncertainties in science that we can quantify is again unique. I was asked recently on some radio program to quantify, you know, the likelihood that there are extra universes. And I said, I can't do that. I won't do that because it's just a guess. The wonderful thing about, if I had a theory, then I'd be able to quantify my uncertainty. And the great thing about science is that we can quantify. We can say that the likelihood of temperature changing between this level and this level has a 95% or 97% uncertainty. And we know that it's not just pie in the sky. We know what we mean by those numbers. And so one thing I've written about, and I'd like to write a lot more about, is writing in praise of uncertainty. Because people don't understand that scientific uncertainty really, everything is uncertain. There's nothing that's absolutely certain. And the fact that science can quantify its uncertainty is one of its greatest strengths, not its weaknesses.
I want to say to the aspiring scientist, also learn how to write winning funding proposals. It's a very good skill to get started. That's one thing.
And learning how to write and communicate, Arnold, let me just 1 second even elaborate on that. I was part of a program later on at MIT when I was at Yale maybe, a visiting committee. And they were talking about integrating writing and communication into the curriculum. Because for scientists and engineers, now it's changing, but for scientists and engineers, too often it's not at all a part of the curriculum. And when they get, you know, when they're forced to do writing, it's some random English professor who no one cares about, you know, some lecturer, and no one ascribes any, they don't ascribe any significance to that person, so they take the course and that's it. If instead the people that they admire, the scientists who are teaching them, say, require writing in the classroom, that would be very different. And it would be very useful because your career as a scientist or an engineer will depend as much on your ability to communicate, not just to the general public, but to your peers and to government funding agencies, as anything else. I have been, you know, as chairman of a physics department for many years, I've seen many young scientists who were quite talented who didn't get the job that we were offering because when they came, they couldn't communicate. And it's sad in a way, but that's just the way the world works. Sorry, Arnold.
So that was just one remark. The other one is my specialization is Earth observation, so I think we should point instruments at the Earth rather than in space. But the International Space Station is finally being used as a testbed for new Earth observation sensors, so it's beginning to have more and more use.
Yeah, but you wouldn't have spent $150 billion doing it. You could have done it much cheaper if you just built a dedicated one.
But the real question I wanted to ask you, let's do mind exercise that 3 people will go on a Mars mission. Would you put 3 atheists on it, 3 Scientologists, 3 deeply religious Christian scientists, or would you put a mix on them?
And that's a good question. By the way, Earth-based observations are sometimes useful for space. As you know, the discovery of gamma-ray bursts, which are this most energetic objects in the universe, was done because of an Earth-absorbing instrument. It wasn't an Earth-viewing instrument. It wasn't for science, but it was for national security. It was looking for evidence of Russian nuclear tests. And suddenly they got gamma rays, which is a signature, and of course what they were seeing was gamma rays coming from the other edge of the universe, and so sometimes instruments designed for looking up can be useful for looking down and vice versa. In terms of who I choose, of course I would want to have to choose. It is an interesting question that arose tremendously after I wrote that piece in the Times. There was more interest than I could have imagined. I did a lot of radio programs. And actually, it got optioned for Hollywood. Someone said, can we option your op-ed piece in the New York Times for Hollywood? I said, why option it? It's in the public domain. You don't have to do that, but they did anyway. They wanted to make a movie about exactly that. Choosing those people and their life story and how they would come together before they went. And then it got silly. There were Martians and stuff. But what is interesting to me was something that was recommended independently in 5 different places around the country when I did radio programs. Was a listener came on and said that what they would suggest was an all-woman crew with vials of sperm. They felt an all-woman crew would deal better with the whole process, and then if you don't need the men, you just need sperm. Anyway, so maybe that's a good suggestion, but I wouldn't. I think that would be a huge thing, and it's not just 3. We're talking about 4, but you've got to have this other question, which is what's the optimal number? You know, because you got this social dynamic situation. You got 3 people, 1 person. We all know what it's like to be the third wheel. You know, there are going to be 2 that are going to be pals, and the other one's going to feel left out, and you've got all these dynamics. And so you got to ask, what's the best group where you can temper individual problems, and how can you test for that in advance? And one of the tests that's used actually, well, many of my colleagues and some of my former students when I was chair have gone down to Antarctica and wintered over in Antarctica. And there are many tests that people give to those people, because in Antarctica you're stuck for 6 months when you winter over. And so they all do all these tests to make sure you're not going to go crazy. And so that would be a very interesting thing to do, but I would presume, since I'm no expert on human behavior, to judge myself.
Now there's been a couple of segue points now, so I'll shift to it. Given your position on embracing uncertainty and understanding that not knowing is actually a good part of the process, and I sat through the screening of The Unbelievers some weeks ago, how do you make that argument to people that are not willing to accept that uncertainty is actually a good thing?
Well, I mean, look, there's certain people you'll never reach. And if people aren't willing to accept arguments or listen to how we can learn about the universe, then at some level, if their minds are so closed that they need certainty, then I think you have to I mean, look, it depends what you're trying to do. When we do a movie like that, or I do a debate, there are lots of people I'm never going to reach, and I just give up. And what I'm trying to do is reach a much broader group of people who are watching, who haven't thought about those issues, and whose minds are much more open, and it may be the first time they thought about it. So those are the people we're often trying to reach when I debate some nutty, you know, Christian apologist or whatever, you know. But I think if you're really trying to reach people, what you do is gently understand where they're coming from. I mean, if you're making an effort to try and communicate, there are always barriers. And so you have to ask, where is this person coming from? What are their prejudices? What are their things that will interest them? What are the things that won't interest them? And use those things to open their minds slowly. That's why I wrote the physics of Star Trek, for example. It's because many people are afraid of science, but they're not afraid of Star Trek. So I can use that. And the other aspect of that book, and which is relevant to much of my teaching and to some extent lecturing, is really the way to reach people is to have them confront their own misconceptions. You can't force it on them. But if you can get them to confront their own misconceptions and realize, you know, if I follow this line of logic through, I come to something that's ridiculous. And that's why Star Trek is so useful, because there's so many misconceptions then I can have fun with that. But I think, so you've got to ask, why are you talking to the person you're talking to? And in public, I'm often not talking to that person because I care about that person particularly. Well, that's not always true, but certainly in Australia recently it was very true. But I'm trying to talk to the much broader audience. But if you're really interested in teaching, you've got to, I often tell teachers the biggest mistake they make is to assume their students are interested in what they have to say. Because that, if you assume that, you've lost them. You have to ask, why should they be interested in what I have to say? Why? What is relevant to their personal life, their experiences, their dreams, their hopes, their fears, that this is relevant to, and try and reach through that. And so, you know, that's a slow and long process, but at least it overcomes that defensiveness that people get when they immediately feel you're trying to threaten their beliefs. If you show an interest in what they're interested in, then people's hackles go way down and you can actually have a discussion.
I actually have a question that's come through Twitter. Chris Barry asks, I think there's a gap in science communication in explaining the what rather than the how. What do you think?
Well, yeah, I mean, I think science is about the how. And if he means we often explain the what, we just give it as a series of facts, which you're supposed to believe on faith. You know, you get told these facts you're supposed to memorize in school, and they're the same as memorizing the 10 Commandments or something stupid. And so we need to understand the how, and how to get to these conclusions. And he's absolutely right, that we don't do that in schools. And one of the reasons I think, and I don't presume, I'm more experienced in the United States, obviously. I suspect it's not that different in Australia. But one of the problems is, I mean, I admire teachers tremendously, public school teachers, because they're the front lines. As my friend Steve Weinberg says, they're doing God's work. And he's also an atheist. But you know, it's an incredibly important role, as well as a difficult role. But the problem is, if you're not comfortable with the material, you'll teach to the facts. You'll teach to the book, because you don't want to ask any kid to ask a question, because you're afraid of saying, I don't know the answer, and that's the wrong attitude. And so I think the problem, the reason we teach the what rather than the how is that the people doing the teaching are not comfortable enough to say, either I don't know, or to know enough about the how. But that's really what we should be doing. I agree. Way in the back there.
What's your take on the different interpretations of quantum mechanics? Do you find you take the shut up and calculate view, or do you think there really is an answer and that we can resolve it empirically?
Well, I tend to take the shut up and calculate point of view for the most part. Because the problem with the interpretation of quantum mechanics is it's misplaced. As someone who's much smarter than me, a friend of mine, a mentor, a professor at Harvard who I knew very well, Sidney Coleman, a brilliant physicist and humorous man, pointed out that we talk about the interpretation of quantum mechanics, but that's exactly the wrong thing to talk about. We should be talking about the interpretation of classical mechanics. Because in fact, the world isn't classical, it's quantum mechanical. The world behaves based on quantum mechanics. So you have this thing that describes the way the world behaves, and say, how can I interpret it in terms of this classical picture, which is just a poor approximation? Well, any interpretation you do is going to, therefore, be a poor, is never going to encapsulate all of the quantum mechanics. So we really should ask, how does the classical world can be interpreted, how can we understand the classical world in terms of quantum mechanics? So when people worry a lot about the interpretation of quantum mechanics, I don't worry so much because any of the interpretations seem ridiculous, but I think they seem ridiculous because we're trying to do the wrong thing. But having said that, the one that, in my opinion, comes closest, the only one that I really think captures the essence of quantum mechanics is the many worlds interpretation of quantum mechanics, which says, if you take it literally, that every time you make an observation, that there are many. Quantum mechanics is not indeterministic, as many people think. It's a completely deterministic theory. It's second-order differential equations with boundary conditions, and they're completely determined. Once you give the initial conditions, the wave function of a particle after some time is completely determined. So there's no indeterminacy. Now what happens is when you measure the properties of that particle based on its wave function, that's probabilistic. Okay? So the particle doesn't have any specific properties before you measure it. Electron is spinning, but it's not spinning in any given direction before you measure it. You'll measure it as spinning in this direction, but it wasn't spinning in that direction before you measured it. It was spinning in all directions at the same time. Okay? Okay, and that seems crazy, but it's true. That's just the way it is. Now, if you want to apply a classical interpretation to this, you'll say that the wave function has many, gives you a probability of measuring a whole bunch of different properties of that particle. It's a probability distribution. And when you do a given experiment, and you do 100 experiments, you'll find that probability distribution to be able to measure it. But in a given experiment, you'll measure it, and it'll be probabilistic. And so what that said, what the argument is that there is many branches of the wave function, and every time you make a measurement, you force the system to be in one branch. You measure the spin to be up. There are an infinite number of other possibilities. And so every time you make a measurement, reality is branching. There are an infinite number of realities. And you follow one, it's like a stream with lots of tributaries. You follow it as you make a set of measurements, but there are a lot of other realities where, where I could be asking you the question and you could be answering it, okay? And so it sounds neat. There's many worlds. It just sounds neat. It does encapsulate the physics of quantum mechanics, but it doesn't operationally change anything, because you can't travel between one. You can't, unlike it often happens in Star Trek, where they do travel between the branches of the wave function, in at least 1 or 2 episodes I know of. You can't access those other possibilities, so it's a nice way of framing things, and it sounds very sexy, but I don't think it adds much. But I think, ultimately, the real issue in quantum mechanics right now, the real thing that really is sort of still not fully understood, is how you get classical measurements from quantum. I mean, it's almost understood. A lot of progress has been made, and I should say this, and I know I'm going to get hate mail for it, it's been made by physicists, not philosophers. There are a lot of philosophers who study the philosophy of quantum mechanics, and some of them have degrees in physics. But the progress has been made by physicists, and I'm just sorry, it's true. And the progress is, how can you go from this quantum mechanical world to the classical world we see, and what does measurement mean? What does it mean to measure something? You're obviously disturbing the system, but at some level. And more importantly, if the whole universe is quantum mechanical, so there is no outside of our universe, what does it mean if you have a closed system that's quantum mechanical? If you're outside a system, then you can talk about measuring it. But what does it mean to make measurements in our universe if it's a quantum mechanical object? Those are still thorny questions that I don't think are fully resolved.
I have a question. So the double slit experiment has been repeated with buckyballs, and people are trying to do it now with viruses. I was wondering if it gets to a stage that, say, bacteria were able to interfere with themselves in a quantum mechanical state, what would that mean?
Well, I think the problem with virus level things is that I suspect they're not quantum mechanically based. And I mean, they're quantum mechanically based, but they're basically large enough to be classical. So in order to have the double slit experiment says if you send a single electron, it starts with a light ray. If you send a single, if you have 2 slits in a screen, and if there are 2 slits in the screen here and I had a machine gun, if I live in the United States where we all carry machine guns, then if I just did the gun back and forth, then I kill the people behind the slits, where the bullets can come through, right? But if I send light rays, what I don't see on the screen in the back, I don't see that. I see this nice interference pattern. And you say, okay, well, the different waves interfere. But it works out if you send a single photon through, a single one, it goes through both of them and interferes with itself. Now, if you try and say, is that really possible? I want to look. You shine a light, and then you'll see the photon go through one slit or the other. And you say, see, it only went through one slit. But then when you look, you won't see the same pattern. Because you forced the photon not to be in many places at once, but in one place because you've observed it. So you've changed things. So the double slit experiment was the real manifestation of the fact that particles like photons, and the same thing happens for electrons, and any quantum mechanical object are doing many things at the same time. An electron is literally going through both slits at the same time, unless you measure it. If you measure it, you can force it to be in one slit or the other. But if you don't measure it, it's doing everything. I often say quantum mechanics is like the White House or corporate America. Anything goes if you can't see it. Okay? And if that's the way it is, so as long as you can't measure it, anything's happening. Now, the question is, at what stage do systems stop behaving that way? Do they behave more like bullets? And the only reason that you get these weird interference patterns is something called quantum coherence. And what that means is that the system really doesn't get affected by outside objects, or even internally. You know, a single electron, a single photon doesn't have internal degrees of freedom, really, and therefore it doesn't mix up the quantum states in any way that becomes classical. When you have a virus, you've got lots of stuff interacting, and it's hard for me to imagine that you're maintaining quantum coherence. I mean, we're all quantum mechanical, but we act classical because our bodies are interacting so complicated that any quantum correlations get washed out in a fraction of a second. And while an electron I could send through that wall, I could bounce electrons through the wall, and every now and then it would suddenly appear on the other side with some small probability. You could do that from now to the end of the universe. Run into that wall with your head first. From now to the end of the universe, and you'll never end up on the other side without creating a hole in your head or the wall. And so it's an interesting question, and it'll be interesting to see. But I would be amazed if viruses, at the level of viruses, are quantum mechanical and enough to preserve the kind of correlation. Now, there may be quantum mechanical processes that are important to life. And one of the big surprises recently is that maybe the process of photosynthesis is more quantum mechanical. Requires quantum mechanical correlations. So things don't behave classically. That a moving photosynthesis is really the process of exciting electrons and moving them around and building up stored energy so they can slide down, be absorbed by oxygen, and that energy is released in your body and does stuff. And what's been interesting is that it does appear that, at least in some plants, there are quantum correlations between processes that happen different times, which is very surprising because the plants should be very classical. So we still have a lot to learn.
Lawrence, what do you think the next big discovery will be in physics?
Whenever I get asked that, I give the same answer, which is, if I knew, I'd be doing it. I mean, that's the whole point. That's why it's called a discovery. It's because we can't anticipate it. Now, there are areas where we know that are quite exciting, and we know that we have whenever we have a new window, we tend to make discoveries. So there are areas of the early universe that we're going to, I expect, will make discoveries in because we have we're building telescopes to look for that. There are areas of quantum computing that are quite exciting. There's a lot of work going on in. I think in the areas of biophysics, there'll be huge developments in understanding how biological systems work from a physical perspective. But I don't know what the discoveries will be, and that's why it's so wonderful. In fact, talking, as Arnold said, about grant proposals, you always lie. If you're active, at least, you always lie when you write grant proposals. Because you tell them what you're going to be doing in 3 years. And if you don't know what you're going to be doing in 3 years, then it's pretty boring. I mean, at least in the field I'm in. I shouldn't say that because there are long projects that require a lot of work. And I don't want to demean those in any way. To do climate science, for example, we need to set up a long pattern of measurements that allow us all over the Earth to measure it. And that's going to be a multi-billion-dollar project that takes many, many years. But individually, I just say what I think I'm going to be doing, but inevitably what I'm doing in 3 years doesn't relate to that at all because there are new discoveries in the interim. You just have to sell it and make it seem plausible when you're writing the right proposal.
Okay, I'll ask a question.
Mm-hmm.
What is it about quantum mechanics that makes it so popular with people like Deepak Chopra?
Well, one of the things that makes it popular with hucksters like him is that people don't understand it. So if you're trying to con people, pick an area they don't understand, and you're more likely to be able to sell, snake oil. The other thing is it's so new agey, right? It seems like we are, connected to the cosmos. That because the observer and the measurement are connected, somehow our brains are somehow connected to the rest of the cosmos, and it pushes all of those buttons. The people who want there to be some cosmic consciousness life. And so people like him can exploit that ignorance of quantum mechanics. In fact, for me it's a sore point because it's the only area of physics that I know where people get built on money. Almost no other. There's perpetual motion machines a little bit. But quantum mechanics is regularly utilized by people who con people out of money and their lives. And the secret, that nonsense, is based on quantum mechanics, and got people going in these tents and dying in Arizona, and also because they somehow could communicate. They felt that if they thought about something, if they wanted something to happen, it would happen, and that's what quantum mechanics says, and it infuriates me. And in fact, to hit a sore point recently, I try not to do this, but I recently read a review of our movie by an ignoramus, and he got mad at the fact that I jumped on a guy here in Canberra, a very nice young man, an Islamic guy, about quantum mechanics. He spoke about it. But I jump on it because when people talk quantum mechanics and they use it for a point, they should understand it. That's all I ask, or at least have a basic idea. But if they exploit it to somehow allow it to seem like there's no reality that's real, then I get mad and I don't tolerate that. Yes, there.
I just wanted to ask, who's your favourite scientist, if you have one, and if you had to pick one through history, and why?
Who's my favourite scientist?
Yeah, and why him or her?
You know, people again ask me that. I don't pick favorites for anything. I almost don't. I don't think that way. I don't rank things in terms of sort of, you know, number 1, 2, 3, or 4. They're all very different. There are a lot of scientists who made incredible contributions, and they're all important in their own way. And so, but it's almost true for almost everything. I get asked my favorite X, Y, and Z all the time, and it's hard for me to answer because I just don't think that way. But there are obviously people who made huge contributions, and they're all well known. It's no surprise: Isaac Newton, Albert Einstein, Charles Darwin. In fact, I did surprise some science magazine a few years ago by saying that if I had to rate, if I was really forced to rate Albert Einstein versus Charles Darwin for the impact and importance of what they did, I'd put Charles Darwin higher. But we physicists did we're much better at public relations than the biologists. And so Einstein has had this cachet. Also because it seems so hard. Biology just doesn't seem so inaccessible. Evolution is really quite simple. So you know, the stuff that seems too complicated for the average person to understand, therefore seems like it's a greater accomplishment. But in terms of the impact of one man changing an entire field through a combination of observation and theoretical ideas, I don't think there are many people that can compete with Darwin.
I had another question through Twitter. Nick Andrew asks, are there any quantum physics experiments we can do at home with readily available materials?
Yeah, sure. See this? This is a quantum physics experiment. This wouldn't work if it wasn't quantum mechanics. It didn't rely on semiconductors and quantum processes. All of modern electronics relies on quantum mechanics. Every single day, the properties of materials, the properties of semiconductors, the properties of essentially every computer chip and every electronic device that governs your life is a quantum mechanics experiment. So if you want to do the experiment, just turn on your iPhone. The fact that it works is a quantum mechanics experiment. Now, if you want to say, can I do an experiment that demonstrates quantum mechanical phenomena? Yes. And one way to do it is with high temperature superconductors. You can get these magnets now that are superconducting magnets that are at a temperature as low as liquid nitrogen will become magnetic and superconducting, basically. And superconductivity which says you can send a current around without any loss of resistance, is an intrinsically quantum mechanical phenomenon. It's, in fact, it's the heart of quantum mechanics. Could never happen classically. And so, if you wanted to take one of these high temperature superconductors and have it levitate, put in liquid nitrogen, levitate off another magnet, that's an explicit example of superconductivity and quantum mechanics. But it's around us every day. We rely on it. It's not so, I mean, it's exotic, but it's the bread and butter of our modern economy. Now we, okay. There goes an early dinner.
Couldn't you just put a cat in a box?
You can put a cat in the box, but the problem is that you only manifest the quantum mechanics until you open it, and that's classical.
I've read recently that apparently every time you quantum entangle two things, you get a wormhole for free. Do you have any sort of comments on that?
Well, yeah, sure, it's wrong.
That's
not true at all. Okay. Not true at all. But quantum entanglement is very interesting, and we use it. It's maybe the basis of quantum computing and secure messaging, and also, unfortunately, also ways to break bank codes for credit cards. It really says that this weird thing that two particles on the opposite side of our galaxy are really not separate. They're really part of the same thing. And so if I make a measurement of one of them instantaneously, and I mean instantaneously, I affect the state of that other one. It's not the speed of light, and it doesn't violate relativity. And the reason is, classically, we think the particles are separated. But their wave function is entangled, only if, by the way, you haven't let them interact with anything along the way between here and the other end of the galaxy. The minute they interact with stuff, they're no longer entangled. But if you very carefully prepare particles, and we've done it 10 kilometers away, 20 kilometers away, where you can instantaneously affect the state of one particle by another. And we can use that entanglement to relay messages, but not faster than the speed of light. But it's fascinating. But wormholes aren't involved. No. And we probably can't create wormholes.
This is just a silly question.
Okay.
Do you watch The Big Bang Theory, and what do you think of it?
Yeah, I do watch The Big Bang Theory, and I've been privileged, but not as privileged as some of my colleagues. They've invited me on the set of The Big Bang Theory, and my books are in Sheldon's apartment, I'm happy to say. And you look on the wall, which I do in every episode. I look for them. But I have not yet been on the show, but I have been there when they've been taping, and it turns out the producers were fans of physics and Star Trek. I originally didn't like the program because I thought it stereotyped, scientists. But it's very clever, and the characters are actually very likable. So I think it's a wonderful program. I really enjoy it.
And what did you think of the movie Gravity?
Of the what?
The movie Gravity.
I thought it was incredibly boring. I just thought it was a 3-hour, 10 minutes would have been great. It was a movie without a point. It was beautiful photography, full of nonsense from a physics perspective, so I couldn't suspend disbelief long enough to enjoy it. But there was no plot. There was nothing interesting. There was just this incredible, albeit cinematography. But I'm amazed at the reaction. After having made a movie, my impression of film critics has changed tremendously in terms of their intelligence. But I can't understand the reaction. It is a beautiful film. It'd be a great film to it'd be a great film to get stoned and go see. I guess I'll say. But I'm sure, just like 2001: Space Odyssey, but that was much more substance. This one was just so silly that to me, the first scene that just had me lose interest was when the International Space Station is bombarded by these, this remnants of this Russian satellite, and it gets hit, and then it falls. But why should it fall? That's not how it works in orbit. In orbit, all things are falling. As long, if it's still moving in the same velocity, it doesn't fall. So of course, our intuition is you turn off the rockets and suddenly things fall. But there are no rockets operating in the International Space Station. It's continually falling, because that's what an orbit is. You just keep missing the Earth. As Newton showed in the Principia, one of those beautiful diagrams in the history of science, if you look at the Principia, a beautiful diagram. He does a diagram of the Earth and then a little mountain, and he shows, you shoot a cannonball with a cannon, and it follows a trajectory and hits the Earth. You hit another one further, it goes down, and the Earth is curved. You hit another one further, it goes down and hits there. And you hit one that's faster, and it keeps missing the Earth. And it's a beautiful image, and it's just part of his genius. Yes? I guess this one looks like you may have another Twitter one.
I'll ask you a better question this time. If the graviton is discovered, or if it's confirmed, what would that mean for quantum mechanics and string theory?
Well, it's a very good question. As you probably know, I've been writing about this a lot because I think we propose the only way that gravitons could ever be shown to exist. Although we haven't yet convinced the referees. Well, we're right, but we haven't convinced the referees. Quantum mechanics is a big problem. Gravity is a big problem in the sense that it doesn't lend itself easily to quantum mechanics. It's the only, and so at a very small level, which is only the level that's so remote that it doesn't matter for our lives and everyday work. But at a very small scale, at some level, if we want to reconcile quantum mechanics and gravity, we need to do something. Because general relativity appears to be a theory that doesn't make sense when you try and apply quantum mechanics. Some people have proposed that maybe quantum mechanics doesn't apply to gravity. Maybe at that fundamental level, the world isn't quantum mechanical. At a really small level. It's not a sensible proposition, but it's nevertheless a proposition that can't be ruled out at this point. There are no really good theories of it that hold water. So we'd like to see that the particle that conveys, in quantum mechanics, every field and every force is conveyed by a particle. So the electromagnetic waves that we see as light that convey the electromagnetic force are made up of a coherent superposition of particles called photons. And the same is true for all the other forces in nature. The weak forces due to the exchange of particles called W and Z particles, and the strong force due to the exchange of particles called gluons. And so gravitational waves we know exist. We've never measured them directly, but we have measured them indirectly, and a Nobel Prize has been given for that because an amazing experiment by an old friend of mine who's at Princeton. An amazing experiment done over 20 years It's basically an orbiting two orbiting neutron stars, a binary pulsar, and if you could calculate that as one, if they're in empty space, the only way that this object, the primary way that it loses energy is by the emission of gravitational waves, and you can calculate in general relativity how it should change the orbital period. And it changes the orbital period by something like 1/10 millionth of a second every year. And what is amazing is that they were able to take out the Earth's, even continental drift on the Earth has to be incorporated in all of these measurements, and the it's just a beautiful experiment Joe Taylor and a former student has made, and they deserve the Nobel Prize for it, because in fact the observations of the change in that period agreed to within 1% of the predictions of general relativity. So we know that general relativity predicts the emission of gravitational waves whenever I move a mass. Whenever I move a mass, I'm emitting gravitational waves. But gravity is so weak that those gravitational waves carry very little energy and are not measurable directly yet. We're creating these big detectors, and some interesting work in Australia is going towards helping build these quantum mechanical detectors that will help try and detect gravitational waves. But no one has, and the physics tells us that gravitational waves are a coherent superposition of particles, which we call gravitons. But no one's ever been able to do a measurement of a graviton. Another friend of mine, Freeman Dyson, has written cogently arguing that there's no terrestrial experiment you could ever do that would actually detect individual gravitons, because the experiment would collapse into a black hole before it could detect the gravitons. Basically, that's the difficulty. And what a colleague of mine, Frank Wilczek, and I showed recently is that the universe can provide such an experiment. The universe can do what we can't do on Earth. It can take a quantum mechanical signal and turn it into a classical observable. And we propose that would happen, and we can prove it's quantum mechanical. So if we see gravitational waves from the early universe, we know they're produced by quantum mechanical processes, and then the gravitons. And that tells us, if that's the case, that really we need to reconcile gravity and quantum mechanics, and we need a theory of quantum gravity, and the one we have doesn't work. So it would be profoundly important in an intellectual sense. I have to say, from a perspective of what it would impact in the rest of science, it wouldn't impact it a lot. That's what I used to get so mad about when my colleagues who were working on string theory in the 1980s talked about a theory of everything. It isn't a theory of everything, it's a theory of almost nothing. Because even if it was, and it's profoundly interesting to me, but even if it is the theory of quantum gravity, which by the way, would be the theory we need to understand t equals 0 at the beginning of time. So from a scientific, philosophical perspective, that's what we need to understand the beginning of our universe, so it's incredibly important. But that process is irrelevant everywhere except at the beginning of the universe. And in terms of understanding anything else in science, it would not help you at all. It would truly give you a theory of the four forces of nature, which would be useful, but it wouldn't help you understand how oatmeal boils or how climate change is happening on Earth. And so we have to recognize that while it's sexy stuff, and it's what got me interested, I got interested in the kind of work I do because it seemed like it was the most fundamental kind of science. And there was this great public relations campaign about Newton and Einstein and Feynman and other people that got me excited, and what I do to some extent excites young people. And that's great, but it's not everything. And so, but it is from a philosophical perspective. If we ever want to understand to truly know what the beginning of the universe was like, then we have to have a theory that makes sense, and we don't have one right now. So everything's just a guess. Even the theories I talk about in my most recent book are educated guesses.
There's been a recent article about a computer model suggesting the universe is a hologram.
Yeah. A lot of you know about that. Well, it's good press. Well, that idea is not new, by the way. It's been around for a long time in string theory. There was a very interesting bit of mathematics proposed by then a graduate student, actually, who's now a professor at the Institute for Advanced Study, Juan Baldacena. And you can show that it's amazing that all of the, just like a hologram, which is a two-dimensional plate, and you look through and you see all the information of the three-dimensional object. So if I took a photograph of this room, I wouldn't see your shoulder because the man in front of me is blocking it. But if I took a holographic picture, then I could go like this and I could see your shoulder. Okay? So all of the three-dimensional information is stored in a two-dimensional plate. So in some sense, the three-dimensional image is redundant. I can store all of that information in a two-dimensional. Right? And what's been shown is that in certain cases, for certain mathematical systems, all of the information you can choose to solve a problem in a four-dimensional universe by treating it as in some cases as a three-dimensional universe with different laws. That the physics is exactly the same, and therefore you could say, well, maybe all of the information on our universe is stored somehow on the surface of the universe rather than embedded inside. But the problem is that sounds nice, but this mathematical equivalence works for only very specific physical theories and mathematical systems. And so and those systems do not describe the universe we live in. Now, whether at some more fundamental level they would is an open question. So it's fascinating from a mathematical perspective, but it's a way of promoting this interesting work. But we have no evidence that the universe is a hologram and that dimensionality doesn't mean, or that there's extra dimensions. It just is a wonderful mathematical tool that allows us to solve some problems in, say, the theory of the strong interaction in 4 dimensions or in 5 dimensions by substituting it with a theory of gravity in 4 dimensions. You can show there's a one-to-one correspondence between those theories. That's amazing. Now, you could show it, and the reason there was an article about this in the newspapers is that it was a lemma. It was a postulate. Maldacena looked at certain mathematical quantities and they seemed similar. And he said there's probably a correspondence. But no one's been able to prove it. And so what these people have done is detailed computer simulations of detailed calculations in the two systems, and the end results are the same. That gives a lot more evidence that theory, that mathematical postulate, as a mathematical fact or a mathematical idea is correct. But it doesn't say anything about our universe.
We talked about the Big Bang Theory, but there's also
the TV show or
the TV show.
Okay.
There's also Star Wars, Star Trek, Doctor Who. Why do you think science and scientific themes are so popular in entertainment?
Well, because there's two. I mean, science fiction has been popular for a long time for a number of reasons. One is, I think because everyone asks themselves that question. Everyone looks up at the stars at night and would love, we want to know if we're alone, first of all. And we all feel terrible that we can't travel to the stars, that we're stuck on Earth. So playing off those hopes that are universal works. But also, I think science fiction inspires people in a way because it frees their imagination to imagine many possible worlds, just as literature does. Literature is inspiring because you imagine a world that doesn't exist. But it's a plausible world that might exist because most of literature, it's some historical or someone murdering someone or whatever else. Science fiction gives you one bit more latitude to create not just a plausible world that might exist, but a plausible world where the rules are different. And we all feel sad that we're constrained, that we can't fly, that we can't do this or we can't that. So we can imagine out there somewhere those things are possible. We also live in a world where technology has changed the world so much that the world today would have just seemed like magic to 50 years ago or someone. And so we can imagine that the world 50 years from now will be magical to us. But the other reason that science fiction, I think, is so wonderful for people is it allows us to talk about things that we couldn't talk about in the context of any other kind of literature because it hits too close to home. But if you imagine a world, and Abbott did when he wrote Flatland in the 1800s. He wrote a beautiful mathematical romance, which was kind of a science fiction about extra dimensions. But what he did was satirize the ridiculous Victorian rules of the day between men and women and everything else. He couldn't have written that in the context of literature. It would have been too tumultuous. It would have been too many historic points. But in the context of science fiction or Gulliver's Travels, he could also satirize the world that we live in by showing how another world is so ridiculous, where people have wars based on which side you want to break an egg on. And so I think science fiction allows that liberty to satirize. The first interracial kiss that was ever done on TV was done in Star Trek. It could never have been done in a Western or in a regular TV show. But it's okay in imagining in the 23rd century because it's a different world than our own. But it still represents the kind of racism that was prevalent at the time. So I think that's another thing that science fiction allows people to overcome.
I just want to ask about supersymmetry in particle physics. It seems to me that theoretical particle physicists talk an awful lot about supersymmetry, and we hear very, very little from the experimentalists. I guess, firstly, how far off do you think we are from experimentally finding supersymmetric particles?
I think, well, supersymmetry is, we hear experimentalists talk a lot about it because they rule it out.
Yeah.
They're limiting it. But the Large Hadron Collider, if you wish, really wasn't designed, it was designed to search for the Higgs, but most of us felt was really, its real likelihood would be maybe discovering supersymmetry. So I think it's potentially a year and a half off when the when the Large Hadron Collider turns back on after being upgraded with higher energy and higher luminosity. It's turned off now, but not because its job is over. Its job is just beginning. And if supersymmetry, which means it's a wonderful new mathematical principle that suggests a lot of new particles in nature, may explain why the Higgs has the properties it does, and it is the basis of string theory. Now, discovering supersymmetry wouldn't tell us that string theory is correct. But not seeing supersymmetry also, unfortunately, doesn't tell us that string theory is wrong, because it could exist at a level we can't probe in our experiments. But most of our ideas suggest that the value of supersymmetry, the things that recent theorists proposed it, was that it solves problems on the scale related to the Higgs particles. And therefore, if it manifests itself in nature, we should discover it by discovering a whole bunch of new particles. We turn on the Large Hadron Collider next. And so it could literally be around the corner. If it isn't discovered, which of course is more interesting, it does mean that these ideas we have about how to understand why the Higgs particle exists the way it does and why the weak interaction is the way it is, those ideas are fundamentally wrong. And as I point out, that makes it more exciting. Especially if you're a young scientist who wants to make a name for themselves by coming up with the right idea. Okay. Good. Two questions. Okay, these two. These two here, yeah. You and then you. Okay, well, I don't know which order. Okay, you first and then you, because you're microphone. Which one do you want? You're the moderator. Okay. I keep forgetting. Okay.
A simple question. I'm listening here, and I've done it a few times, to you talking about particle physics and quantum mechanics and all that. And what I find is that it all sounds very nice, but I can, at some point, listen to that and say, is that the way I'm just imagining something I don't understand, actually, without going, do the math and do the hard yarn. And is there actually any interpretation that is acceptable in general, or does every physicist have to build their own picture in their mind, and there's actually no requirement to have the same picture, right?
No, we all have exactly the same picture, and that's why it progresses and it works. Started with something called Schrodinger's equation. It describes, for non-relativistic particles like electrons around certain atoms, exactly the atomic energy levels of atoms. It makes the best predictions in all of nature. Not quite the best predictions, because it's wrong at some level, because the electrons behave relativistically, so you need a relativistic quantum mechanics. We created such a thing called quantum electrodynamics, and that is a theory we all use, and it is the best scientific theory in existence. It's the only scientific theory that allows you to make mathematical predictions and compare them to experiment to 14 decimal places on the basis of first principles. There's nowhere else in science we can do any calculation on the basis of first principle science and predict a result of 14 decimal places. That allows us to do it. We all use it for that reason, because it works. So we all speak the same language, and that's really important. Everyone, different cultures, different religions, different languages. We all communicate using exactly the same language of mathematics, and that's why the Large Hadron Collider, which was built by physicists from over 100 countries speaking dozens of languages, and again, dozens of different cultures and religions, they all spoke the same language, because science, unlike religion, science unifies us. Science puts everyone on the same page, because we're all subject to the same laws of nature. And it's a wonderful example of the way that humans can coexist, function, and work together and respect each other, independent of any of those other human frailties. I find that's, to me, one of the greatest aspects of science, is that it gives an example of the fact that humans can transcend all of the myopia that is inbred in us from a personal perspective, a cultural perspective. We can overcome that at some level, maybe not in our entire lives, but at some level, and work together. And I think that's just wonderful.
And just follow up.
Well, 1 second. Yeah, okay, you can continue for a second.
I understand, and I know the math can work, and there's a common language, and everything works. But when you close your eyes and think about it, you're thinking, at least okay, I shouldn't say you, I'm thinking in a classical way. So when you say there's a double slit experiment, I think double slits, and all that, and say the wave function goes there.
Well, forget the wave function.
Well, actually,
you can picture classically. The electron is doing everything at once. Every time an electron goes from here to there, it takes every possible path in the universe at the same time. That's the classical picture, and it works. It goes to the moon and back.
That's what mathematics says, but the question is...
No, physically. It's not mathematics. We can test that. It's physically doing everything at once.
Yes.
It is going to the moon and back.
I mean, there's a mathematical description, but I find that it's difficult to actually imagine it in a classical way.
Oh, it is. It's difficult for all of us.
Stuff you don't see.
Well, I know, as some of you know, I wrote a book by Richard Feynman, and Feynman said if you think you understand quantum mechanics, you don't. In fact, Feynman, won the Nobel Prize for his work in quantum electrodynamics, and I named the book Quantum Man. But he actually was quite interested in quantum computers, and his argument for it was, if I can make a quantum computer, maybe I can understand quantum mechanics, because I don't now. So it was interesting. Okay, any final question? The back there.
Oh, the pressure to have the last question, it better be interesting, isn't it? So if you had a couple of $1 billion at your disposal to spend on particle physics, where would you spend it?
That's a great
Well, I think the best bet right now is the Large Hadron Collider. I think it's the best. Now, there are other places you can look for interesting effects. You do with neutrinos, for example, which are still my favorite particles in nature. But unfortunately, some people think that we want to spend money just because we want to spend money. But unfortunately, the laws of physics tell us that the only way to explore nature on very, very small scales is to have a lot of energy. It's a property of quantum mechanics, the uncertainty principle. To resolve things on small physical scales requires a lot of momentum and then a lot of energy. It's just a law of nature. And so we have no choice but to build higher and higher energy machines. There's no way around it. Now, we may, as things continue, our waves of accelerating particles get smarter and smarter, and we may do it for less. But the Large Hadron Collider is the most complicated machine that humans have ever built. It is amazing that it works. It is unfathomable, almost, that it works. And to think about the fact that it's 26 kilometers around with superconducting magnets that are bigger than any of the magnets you find in MRI machines or anywhere here. 26 kilometers around, superconducting, so that means the temperature in that tunnel has to be colder than the temperature in outer space near the Earth. The vacuum in that tunnel has to be rarer than the vacuum near the International Space Station. We create a vacuum that's better than space, that's colder than space, that operates with superconducting magnets over 26 kilometers, accelerating particles at 99.999999% the speed of light in different directions. Each instant, the collisions produce more information that are detected by the detectors. Over 1,000 terabytes of information in each set of collisions, and there are 1 million collisions each second. More than the information contained in all the libraries on Earth. And how to sift through that and throw out almost all of it in a way to find out what's happening is amazing. It's amazing that we can do it. And so I think it's not just, of course it's esoteric. And of course it's expensive, but in a global sense it really isn't expensive, right? $10 million over 20 years in a global sense is, is less than, as I point out, the air conditioning bill in Iraq during the Iraq War in a week. Okay? So, it's a lot more useful. And so it's esoteric, but it's not that expensive in a global sense. And it's humans pushing technology and their abilities to the very limits. And whenever you do that in any area of human activity, you're going to benefit. And even if you discover something you didn't expect, or even if it's just creating technology like computer technology, like the web, which was of course created at CERN, because you have 1,000 physicists in different parts of the world that need to work on the same data without knowing where the computer is. It has to be invisible, and that's how the web was created. So, but I don't believe in justifying these experiments by their side benefits, and unfortunately we've done that too often in particle physics and in space. If it's interesting, you've got to convince people it's just worth doing for the sake of doing it. But anytime you build that kind of technology, you're going to produce breakthroughs that are going to trickle down in the rest of the world for years to come. So it's not very original, but the Large Hadron Collider still, I think, is the way I would spend that kind of money. And we don't have to spend it for the most part. It's already been spent. Still, we have to maintain 5,000 scientists working long hours, and but you know that's good for the economy too.
Okay, on that note, I'd like to bring the lecture to a close. So thank you very much, Professor Krauss. Who'd like to make a presentation, I believe?
What? Who, where, what? What's happening?
I'm so sorry. Can I bring my alumni up with me?
What's happening? Oh, presents.
We'd just like to thank you on behalf of the National Youth Science Forum. Professor Krauss has been a supporter of ours for some time, and we have 2 new T-shirts in our range.
It looks like they're being modeled as well.
These are 2 of our alumni.
I love these T-shirts. And Iron Man. Well, this is great. This is great. I have 2 people that are very close to me here in Canberra who are going to really love wearing these T-shirts.
Thank you very much.
Thank you very much. Thank you very much. Thank you.
And on behalf of Canberra Skeptics, I'd like to give you this as a token of our appreciation for coming to speak to us again. So thank you very much. Okay, ladies and gentlemen, well, that brings the lecture to a conclusion.